All right, hello, and thanks for coming in. I know C++, it might be a little different than a lot of the talks here, but we love C++. It runs all of our browsers, our operating systems, all that stuff, right? Our drivers, our libraries, so much C and C++ still out there. So the talk I'm going to be doing is on use after free exploitation, and most of you should be well familiar with that term. The idea behind it is as objects are created and then they're deleted, if they're deleted prematurely, what happens if someone goes to reference it? So it's a big topic. It's like the de facto exploitation technique against browsers and big applications like Adobe Reader and others, because it's once you find them, it's relatively easy to determine if it's exploitable. And if it's exploitable, you can make a lot of money off of it. So for example, I'm just throwing some random numbers out there that I've experienced or peers of mine have experienced, where you could quickly make $10,000 to $25,000 from a single use after free trigger, depending if it affects IE 8, 9, 10, 11, or Chrome or some other browser out there. Each one has a price tag, especially depending on what you can do with that particular bug. If you can get remote code execution on a browser, it can be worth a lot of money. If you can come up with some new novel technique to do things like bypassing exploit mitigations, like ASLR you may have heard of, then it can be worth up into the six figures. So I know a lot of people who have been making six figures every year on this type of attack for years now. Microsoft has done a lot of work recently. You may have seen the Patch Tuesday in June and July that they tried to put some more exploit mitigations in to remediate this issue. But anytime you do an exploit mitigation, you're typically treating the symptoms and not the root cause. So the root cause, the bug in the code, is still there. So that's kind of what we're going to talk about here. Just real quick, I teach for the SANS Institute for quite a while now, and I'm also an author on advanced exploitation and advanced pen testing courses are the ones that I do. I live out in San Francisco as a consultant. And I joined this new site called Twitter a few months ago. I finally decided to join, so I'm up there now. Don't have many friends yet, but it exists when released memory, freed memory, is later referenced. You may have heard the term dangling pointer or wild pointers. They have different meanings depending on who you ask. But typically when you say dangling pointer, you're talking about a use after free scenario. It's mostly a C++ problem, but again, our browsers are mostly C++ based. We have JavaScript that needs to be able to access the DOM and manipulate things in order to cause these triggers to occur, to cause the reference to later occur. So it can often be controlled or used to control the instruction pointer, to get code execution, which of course is at the end of the day, something an attacker highly desires. So it's been very, very lucrative. I've given examples of the kind of money that you can make off of it. It does require a good understanding of HTML, DOM, JavaScript, and of course some C++. So let's talk a little bit about it. I've got some diagrams. I'm going to do some presentations. I'm one of those crazy people that likes to go and test the demo gods all the time, and I get in lots of fights with them, so we'll see how it goes. So C++, if you're not familiar with it, if you use virtual functions within a class, something gets created called a virtual function table. This virtual function table holds pointers to virtual functions within that class. So if we instantiate an object out of a C++ class, then various virtual functions can be, of course, called. The way that works is the first double word, so 32 bits, or quad word, 64 bits, depending if it's a 32-bit browser or 64-bit browser, in that instantiated object is a virtual pointer. The virtual pointer is a hidden class member that's created at compile time. So every object that gets instantiated out of the class is given this virtual pointer as the first double or quad word. That's important because when we go through the process of calling a virtual function, that virtual function vPointer, you can call it, gets dereferenced out of the object. And I'll demonstrate this soon. So we dereference the vPointer out of the object, and then we dereference an offset from that vPointer into the virtual function table to load the desired virtual function, and then we eventually call it. The second double word or second quad word is something called the reference counter, which becomes very important, and I'll explain why in a moment. A class constructor, so with C++, you can create a constructor. If you don't, a default constructor will typically be created. When an object gets instantiated, it goes through this constructor function, which creates it. It's got a size associated with it. The memory is allocated, all that good stuff. Just like everything gets created, when it's no longer needed, it goes through a destructor, so it gets destroyed, I guess you could say. If you're talking about things like C++ smart pointers and others, you've got this thing called a reference counter, and that's the second double or quad word in the object. That reference counter, when you instantiate this object, it gets incremented to 1. And every time a new reference is made to this object, it gets incremented again. Every time it goes out of scope or we don't need it anymore, then we decrement the counter. When that counter gets decremented to 0, that's when the object can be released. If the object gets released prematurely and something comes to go reference it later on, thinking it's still there, that's when you get a use after free scenario. I used to give this terrible analogy. It worked in my head, but that doesn't always mean it works for everyone else, about how to explain use after free. And I had my dog passed away recently before this, and I was like, let's say you still have a reference to the dog, and the dog dies, and you come home and it's not there, but someone replaced it with an angry pit bull, and it didn't make any sense. So I'll use a different one, which is, imagine if 6 people go in on buying a 6-slice piece of pizza. So you've got 6 slices. 6 people go in. Each person gets 1 slice. But one person, they have 1 reference, each one. They've added that reference. What happens if one of those individuals eats 2 slices? They've decremented now prematurely down to 0 because the 6th member didn't get their slice. Someone decremented it prematurely down to 0. So what happens when this individual goes to get their slice of pizza thinking it's still there? If it's not there, they're just going to be angry, right? If it's been replaced with a malicious slice of pizza, you can think about, I went to Casa Bonita last night. It's kind of on my mind. So I waited 10 years to go there, right, after the South Park episode. So, but you get the idea. Something that's supposed to be there is prematurely deleted, and therefore, what happens? Well, if we can replace that object with something malicious, then we can get control of that user's browser and hopefully their system. So replacing the deleted object, it allows for control. So this object, remember the first double or quad word I said is the V pointer. Well, what if we could somehow replace that object that's been freed, and then we can trigger the use after free bug so that object gets dereferenced, the pointer out of it, but it's now our pointer. That means we get control of processor registers, and we can tell it what to do at that point. So in this example, we're replacing a 56-byte object. You can see up here we're using unescape, so we want it to be dead code. Because what usually happens is, and I'll have a diagram coming up soon, we dereference the first double or quad word out of the object, and it goes into the designated register. We want to make sure, because the way Unicode works and such, that there are no nulls in here. So we need it to be 56 bytes in this example. So we have our first 4 bytes on escape. That's going to be our pointer, our V pointer. Then we've got the padding bytes to fill us out to 56 bytes, minus 2 bytes, because there's 2 nulls that get put on the end automatically. So in this example, we padded out 25 bytes, but we say times 2, because each of those bytes is going to get a null added onto it. So in this example, we're up here. You can say we're creating a variable called vtable, and we've set it to be what's on the diagram on the lower area. We want dead code to be loaded into the designated register. Then we allocate memory here in the second line. Down here at the bottom, you can see we assign it equals vtable1, so we're able to get that allocation that we want and fill it with exactly what we want. Now, Microsoft recently tried to stop some of that, because one of the big issues is a lot of these objects, when they're created, are created in the process heap. So that's the general, if you're familiar with memory, the general process heap that the process has, like Internet Explorer. So they created something called isolated heaps, which is nothing new in security. It's just new to Microsoft's browser. The idea behind isolated heaps is, let's make it so it's not so easy for an attacker to allocate an object at a very specific location. If we isolate things in their own heaps, then how is the attacker going to get that allocation into that specific heap? Or is it just going to end up in the process heap? So we're not going to be able to replace the freed object as easily. But there's a lot of research now going into, well, how do we fix that? As an attacker, how do we make that still work? So this right here is a common exploitation technique for use after free. We do something you may have heard of called heap spraying. Heap spraying, the old technique was we use JavaScript, we run a little loop, and we just keep allocating huge amounts of memory, huge blocks of memory, filled up with nothing but something like 0C over and over and over again. And then at the very bottom of each allocation is our shell code, to open up a port or something like that. The 0C serves a couple of purposes. One is with the default process heap in like Internet Explorer, even with address-based layout randomization running, if we keep forcing allocations to occur, it will eventually hit some predictable memory addresses. So you can randomize all you want. If I can just keep spraying memory with something, I'm eventually going to extend it out to a location that I know is reliable. So 0C was used commonly, and there's a couple of reasons for it. One is we could always extend out to the memory address 0C, 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 0C. And then also 0C is an opcode. It's an x86 opcode, which means OR AL. AL is the accumulator low register, part of EAX or RAX, and it's benign, meaning that if the processor goes to execute the instruction OR AL, it just slides down to the next instruction, to the next one, to the next one, and eventually hits our shellcode. So in this example, we say move into EAX, and then here we're dereferencing ECX. ECX is commonly the object pointer. So the object pointer is being, or the V pointer is being dereferenced out of the object, and we grab right here 0C, 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 and we load it into the EAX register. EAX now holds that value, which is serving as a memory address because we've sprayed memory so far. The next thing that happens is we dereference an offset. So the process thinks that EAX is pointing to the real virtual function table that holds virtual functions. But it doesn't, because we've hijacked it. And we've sprayed memory enough so that memory address 0C, 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 0C points to nothing but 0Cs. So what this means is, right there you see EAX plus 30 hex. That's an offset from the virtual function table's 0 position to the desired virtual function. But as you can see, what if we said EAX plus 0, EAX plus 4, or plus 4, plus 8, plus 12, plus 16, plus 20? It doesn't matter where the dereference occurs, what offset it occurs at, because it's always going to load 0C, 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 0C into the designated register, which in this case is EDX. So now EDX holds that address. The next thing that happens, and you'll see this in a demonstration soon, is we see the instruction call EDX. Whatever address has been loaded into EDX, which is supposed to be the virtual function, is now 0Cs. So we call it, meaning the instruction pointer jumps to this location and starts executing 0C, 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 and slides all the way down, and we get control that way. So that would be taking it from a trigger to actual code execution. So some things we need to do. We need to prepare the heap. That's often done by a heap spraying. In modern versions, we can do something called the DOM element property spray, which is something that Corland Coder or Peter van Ickhout had coined the term of. There's also ways that you can create very specific size objects. I mean, there's many different ways we can do it, and I'm going to explain a couple. But we need to prepare the heap somehow. We need to cause the object to get deleted prematurely. So however we found it through fuzzing or whatever, we found this condition. We need to force that object to get deleted prematurely. So that way we can replace it. Once we've replaced the object successfully, we can then trigger that UAF bug. That means the person who wants that slice of pizza goes to get it at that point, and it's been replaced with a malicious one. So how do we get from a browser crash? Because you've seen it before where a browser just crashes and says, sorry for the inconvenience. We're going to restart. It's easy when you talk about things like stack buffer overflows. I mean, those are like, you can see things very clearly in the processor registers that allow you to determine if it's exploitable. Something that has to do with the heap, like a use after free bug, it's not so obvious when it crashes. If you are debugging, you've got your post-mortem debugger or whatever it is set up, what you see is not necessarily that helpful. So we're going to talk about some quick ways you can determine if it is a use after free bug and how to know if it's exploitable, because that's what's going to get you, of course, the money. So real quickly, before we go into the demonstration, I'm going to go over to IDA. So how many of you used IDA Pro before? It's a disassembler. Awesome. So it's a disassembler that many of you have at least heard of. It's a fantastic tool for producing what's called dead listings. It takes a compiled object and it disassembles it, producing a dead listing. It's called a dead listing because it's not actively running like in a debugger. So what you see up on the screen, and I'm going to zoom in when appropriate. I don't expect you to read that. Over on the far left, that's the function window. It's all the functions within that particular file. Right now, it's mshtml.dll, one of the largest DLLs in your system and heavily used by, of course, browser. So in the middle here, just to make it fast, I I used a tool that was acquired by Google called Zynamex BinDiff. So Zynamex was acquired a couple of years back by Google, of course. They buy everything. There was that funny article I saw on LinkedIn. I always think of it when I'm doing lectures like this. And it said something to the effect of, the developers that work at your organization are there because Google didn't want them. It's like, oh, ouch, okay. But they buy everything that's cool, right? So they bought Zynamex, which is fantastic. They make fantastic products. One of them is BinDiff. BinDiff is a binary diffing tool. What it does is allows you to take a before and then after and diff it. So we're all familiar with diffing tools, but this one's special, and there are free ones as well besides BinDiff. BinDiff's just very good. That takes each function and it does a comparison against them. It identifies the blocks inside each function and tells you where code changes were made at the assembly level. So therefore, it allows you to, let's say Patch Tuesday comes out, you can take the most recent version of a DLL or a driver or whatever, and you can diff it against the one that just came out in the patch. What you should see is very few changes, hopefully, that pertain to the fixes in the code. This is called a one-day exploit or one-day attack, because 0 day is when we've discovered something through fuzzing or whatever, and no one else in the world knows about it that we know of. And we can either use it for profit, we can sell it, we can disclose it responsibly, whatever we want, but no one else knows about it. One-day exploit typically comes in where a vulnerability is privately disclosed to Microsoft or Oracle or wherever, and the security researcher who disclosed it gives the vendor a chance to fix it. It gets fixed, the patch is available, but no technical details are ever disclosed, typically. When that's the case, it becomes lucrative for an attacker or a researcher to do a diff against these files. Because if I can, in 1 or 2 days after the patch comes out, identify the fix and write an exploit to trigger it, then that means people who don't patch right away are going to be vulnerable still. And I don't know about you, but in my experience as a pen tester, not many organizations patch the day the patches come out. Some take a week, 2 weeks, a month, or more. So what I'm going to show you here is this particular function. Let me zoom in. This function right here, C markup is the class, insert element internal is the function in that class that had a problem. And I'm going to run a diff against it. Well, we've already run a diff. I'm going to bring up a visual diff now. What this is going to do is produce a graphical layout of the function side by side. So that's the function side by side, and all those squares or rectangles are blocks. There's a block within that particular function. Blocks typically have something like a conditional branch or jump at the end of them, some kind of unique entry. So the blue ones are identical on both sides, and where you see things like yellow or that purplish bluish color, that means there's code changes there. It might mean that the block didn't exist on the other side at all, or it might mean that code inside that block has changed. So of course that's where we want to zoom in on. So I'm going to show you real quickly, because obviously we only have a little bit of time here, the bug that got patched in this one. So notice here on the right side, so the right side is the patched version, and the left side is the unpatched version. Notice right there where it says add ref. It says call add ref C3POS. That is not, it doesn't exist on the unpatched side. That was where the patch was changed, because in the unpatched version, there was no call to add ref. And if there's no call to add ref, but a reference is there, what happens when it goes and deletes, but it never did a reference in the first place? It decrements an object counter that it never incremented. Therefore, someone else out there who needs to reference this object, they may not be able to do it, and you trigger a use after free bug. So this is where this particular one was fixed. So just keep at the top of your head, insert element internal, because you'll probably see it again here in a moment. So I'm going to go in first. This is Internet Explorer 8, and then I'll do an example or demonstration on 10. I just saw an article the other day that said Internet Explorer 8 is still the most commonly used browser in corporate America. And that's crazy. Internet Explorer 8, it's old, but it's still there in a lot of places. So what I'm going to do, I've got a postmortem debugger set up, which means WinDebug will catch any exceptions that get thrown if the browser goes to crash. So I'm going to double click on this thing called MS13038 trigger. This particular bug was the one that came out last year that affected the Department of Labor website. You may remember it. FireEye discovered it being used in the wild. They didn't discover the bug. They discovered that it was being used. So it got discovered. It was sitting there on a web page in Department of Labor. So anybody who visits it using Internet Explorer 8 is compromised. All you have to do is view the page, and code execution occurs, which is, of course, kind of scary. So I'm going to double-click on this, and it crashes. So there's my postmortem debugger that came up, and I'll zoom in here. What you can see up here is that the instruction pointer is pointing to question marks. It's kind of like Scooby-Doo. There's nothing there. So what is it going to do? The instruction pointer went to execute code at something that has no code there. It's not mapped. The virtual to physical mapping doesn't exist. So just by looking at this, I mean, you can look at the various registers, EAX, the accumulator registers, the count register. I don't see anything obvious. It's not like when we cram a bunch of A's into something and we see a bunch of 41, 41, 41, 41 show up everywhere. We don't see very much. The tool that you typically want to use at this point is something called page heap, which comes with gflags tool that's part of Visual Studio, or the debugging package. So page heap, what that's going to do, we're going to turn it on, and normally a page of memory, if you're familiar, is a 4K. One page of memory is 4 kilobytes. So normally there is many different allocations within that page of memory that's been allocated. Right? We're talking about a physical page of physical memory, and then we've got a bunch of allocations that occur that eat up portions of that page. If we gave every single allocation that came in through a browser, for example, just create this HTML object, and we gave each one of it 4 kilobytes, that would be a waste of space, a waste of resources. But what page heap does is it gives every single allocation its own page of memory. That allows it to have much more control of doing things like setting up special patterns, prefixes, suffixes, and it lets you know if there's any corruption on the heap with your application or an application that you're testing. So that's very useful to us, because normally we can't see very much just by doing this. So I'm going to go turn on page heap and watch what shows up when we hit the postmortem debugger this time. So I'm going to drop out of magnifier so I can actually see what I'm doing here. So page heap, to turn it on, I'm going to say gflags exe/p/enable, and then you give it the name of the program, iexplore.exe. So now it's on. So we'll go back and run the same exact trigger. Here's our postmortem debugger. And now I'll zoom back in. Now look what showed up in EAX this time. That was not there the last time. F0, 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 F0 is a special pattern that's been put in by page heap. What it indicates to me is that the object that was dereferenced there has been freed, because that's the free padding that it uses. So I'll show you some examples of this in a moment. And you can see something very useful at the bottom here. This instruction says, move into the EDX register EAX plus 70 hex. Or remember I explained just a moment ago that the V pointer gets dereferenced out of the object, and then we dereference an offset to that to load the virtual function address into the designated register. That's what's happening right here. So you can see move into EDX. We're trying to load a virtual function into EDX. But since that object's been freed, page heap went in and reset the memory, initialized it to F0s, and it's indicating to us that that's freed memory. So we still would want to go further to determine that it truly is a use after free, and that's what we're going to do next. But I wanted to point that out because it's very useful. Another thing that's useful here is at this point, if we type in UF C element CDoc, C element doc, sorry. And why this function? Because right here it tells us that that's where the crash occurred, right? And it still doesn't like me because I didn't put in. So here we see the dereference for the virtual function that we just crashed at. So this is exactly where we just crashed here. Just before that, you can see this was going to ECX, dereferencing the V pointer and loading it into EAX, and then you see the call. So it's exactly what I showed you on the diagram just a moment ago. It's what's occurring here. So if we go in and say, bang, heap minus p minus a, ECX. ECX is the object. What this shows us are interesting things like the call chain to where this object was deleted at. Right down here you can see C generic element, scalar deleting destructor. There's scalar, singular, and vector, plural, deleting destructors that the compiler, Visual Studio, will create. So we see that C generic element is what's responsible for destroying this object. So therefore, where there is an end, there must have been a beginning. We're going to go in IDA real quickly and look at that class to see if we can find the whatever created this object to begin with. So we'll jump out of here back to IDA. And we're going to go to C generic element to that class. So here we see scalar deleting destructor, which is exactly what we just talked about. So if we double click on this, you can see inside here that heap free is being called. So that's where we're freeing that up. Where there is an end, there must be a beginning is what I just said. So if we go back over here and look at this class, you can see there's one called create element. If we double click on this guy, we can see that heap alloc is called. So that's allocating the memory. This right there is the size of that object. The size is something that we need. So 38 hex is the size of the object, because when that gets freed prematurely and we want to replace it, we need to know that size in order to do that. So that's useful to us. What I'm also going to do in a moment, if we have time, is set up some special breakpoints to confirm that the use after free bug that we're talking about actually exists. So if we go back over to WinDebug, we're going to look at the page heap, what it does here. So here we're going to say DT because we want to dump out the structure. DPH, block information. ECX, which is the object, minus 20 hex, which gets us to the start of the metadata. So these are special start stamps and stop stamps. They help you know that you're in the right spot, because if you don't see these stop and start stamps, then you're in the wrong place. Down here we see that requested size, which matches exactly what we just saw in heap alloc. So that we've confirmed that now. You also see some other interesting things here, like what heap you're a member of, because a lot of applications, when they start up, might be 20, 30, 40 heaps that get created at once. Down here we can see stack trace information, lots of useful stuff to look at the call chains to figure out how did we get to this location. So now that we've confirmed that, I want to show you, let me see the time real quick. I want to show you real quickly how you confirm that it is the object that we're referring to, that use after free bug actually exists. So to do that, I'm going to cheat so I don't have to type the whole thing out. And I'm going to grab a couple of breakpoints. Now these breakpoints are the locations in IDA that we already saw. What these breakpoints are going to do, let me load them in there in a moment here. So first I'm going to start up the browser. That's loaded up. Now I'm going to go up and attach to it. Instead of waiting for post-mortem, I want to see some things that happen during the process. So we're going to attach to sysfader. Let's try it again. Well, let's see if it lets us do it. So I'm going to go ahead and let it run. And we're going to go ahead and visit the malicious page here. The browser's crashing already. It didn't even do anything. I'm having a problem with this guy right now. So what I was going to show you with this one, I'll just jump to the end part. But what I was going to do is just show you created object, was going to give it the address, deleted object, give the address, and then once the use after free condition hits, you'll see that the register where the crash occurs holds that same address in there. But I don't want to spend much time on this because it's not that important. This right here, if we bring up the actual code for EIP control, or actually EAX control, this is the JavaScript, the actual trigger information in here. So this part right here is what's causing the use after free bug to get triggered. Down here, this is where I'm creating that object we saw earlier. So I'm creating an object that's 56 bytes in size because that's what we talked about a little bit more. That is going to show us that dead code, DEADC0DE, which is right here, is going to get dereferenced out of the object and find itself into ECX or EAX. We'll see. So when we run this, postmortem will kick in. So we still got F0s, which means I need to turn off page heap. Page heap is great for debugging this stuff and finding things, but when you're ready to actually start exploiting, you've got to turn it back off. So I'm going to go ahead and turn that off here. So we'll change it from enable to disable. And run the trigger again. So this time, I know it's kind of small, but you can see dead code is at that location. That means that we successfully replaced the object so that when the use after free bug got triggered, that it dereferenced our malicious object. And that's what we want. What we would typically do now, I don't have time to go through all this, but this gets into more of the exploitation stuff, is that we'd have to spray the heap or do something to treat the heap where we point EAX to a predictable location that we have control of. And we put in there at the appropriate offset something called a stack pivot gadget. A gadget is something with return-oriented programming. If you're familiar, we need a stack pivot. We need to take the stack pointer away from the stack and swap it with EAX. EAX right now is pointing to our malicious VF table, our virtual function table. So if we pivot the stack pointer away, we can then create a ROP chain that goes through and disables data execution prevention. We're getting around ASLR by spraying the heap, and in this example, using static modules from Java runtime environment that aren't randomized. So to demonstrate just the exploit working, I'll go ahead and run the actual exploit. First thing we'll do is check and see if a port's open. So it's a 4444 is what the shell code will open. You can see it's not open right now. But if we double click on the exploit, which includes the heap spray, port's open. So all the person has to do is view the malicious page, and because of the use after free bug, we got remote code execution on their system. Of course, commonly this would be something like a dropper file would be dropped on here now, and we'd have some persistent malware installed on the box. So that should demonstrate how powerful it is to find these, and that's why they're worth good money. Like I said, $10,000, $20,000 is easy to get if you're selling to a respectable company for proper disclosure. If you go a different route, you can make a lot more money, but your buyers are going to be different. So real quickly, I'm going to go to a different snapshot I have here. This is with Internet Explorer 10. So this is a much newer bug that came out this year. This was Operation Snowman. It's what FireEye called it because there's a big snowstorm going on or something like that, and it affected, I believe it was the like Veterans Office and things like that, Veterans Affairs. So let me jump out to the slide briefly. So real quickly, ASLR. How many have heard of ASLR? Pretty much everybody, right? Randomization is a pain. When you're doing attacks and exploits, randomization means that when something's where you are used to having it and it's not there, it's like when you're home and your roommate, your wife, your spouse, whoever, you go to find something, you know you put it somewhere and it's not there anymore. That's ASLR. But every time it moves to a new location, and there's something called entropy that's involved, which means there are more locations where something could be stored. If I know I lose my keys and I know they're in the house, it's not too bad. If I know they're in the city of San Francisco, I'm in a lot more trouble. So ASLR is very powerful if everything is randomized. In this example, I'm going to try and demonstrate real quickly, everything was randomized. So how do you then exploit it if you can't find your code, if you can't find your ROP chain and things like that? You need to have a memory leak. There's got to be some type of memory leak, and a lot of exploits nowadays require two vulnerabilities at the same time. There's something called a relative virtual address, and that means relative to the base. Right? If I am a silly example, if I start at offset 0 at the bottom of my feet, and I say at +1 foot is my knee, I know, I may be standing at different locations all the time, but I still know, as long as I know where I'm standing, that +1 foot is where my knee is going to be. Again, silly example, but that's the idea behind this. If we can leak out memory that shows us the base address of where a DLL has been rebased to, then we can use those relative virtual address offsets to populate our return-oriented programming chain, our gadgets. So that's the idea behind it. And this just shows a quick example where we leak out something. This address leaks out, 66FE2104. We can assume or infer that 66FE is the handle, the way that Microsoft rebases things. So 2104 is the RVA, the relative virtual address offset. So we can subtract 2104 from the full linear address, and we get the handle. Now that we've got the base address, the handle, we can auto-populate our ROP gadget locations. So this one, 2014-0322, is a CVE, a newer bug. One of the cool things it did was it checks to see whether or not EMIT is being used, the Enhanced Mitigation Experience Toolkit. It goes to check a path using JavaScript and such to see whether or not a library is there. If that library is there, the exploit knows that you're using EMIT and that it won't be effective, so it doesn't try to exploit you. Pretty neat. EMIT can be bypassed, of course. You may have seen research by folks like Jared DeMott and others who were able to successfully get around the 5 or 6 ROP protections, runtime protections that Microsoft put in with EMIT. So this is an interesting one because we have to do a spray again, a heap spray. I talked about this, just constant allocations. And if you heard of Chris Valasek, he did a great presentation on IE 9, 10, and 11 string allocations to talk about how JavaScript with JScript 9.dll changed the way the allocations occur to be much more efficient. So instead of wasting resources with substrings and concatenations and such, let's just update some pointers. But there are other ways that you can get these allocations. In this example, we're using Flash. So a Flash module written in ActionScript compiled, and inside that ActionScript, it sprays by creating a bunch of objects, memory. It sprays to heap. Again, getting us to a predictable location. This one's neat because normally the array length or the vector length is very small, giving the ActionScript limited access to memory. But the use after free bug in this one is used to overwrite a byte at this location, changing its size from something very small to something very large. Now that the ActionScript has access to more memory, it parses through looking for string matches to find the base address of Flash, and then auto-populates the ROP gadgets and does all that stuff on the fly. So that's where stuff gets really cool. I mean, again, ASLR is completely bypassed through this technique. So let me do a quick demonstration. I know I have a few minutes left here. To do this one, I got to go over to my Kali Linux box and set up a little web server. So I've started up a web server here. And from this guy, I'm going to bring up the browser. And just to show you, it's Internet Explorer 10 right there. And we're going to go to that address, so 192.168.214.129. So when we go there, you can see some files in here. Trigger is one of them. That's the actual HTML that is going to call up the malicious Flash object that we wrote in ActionScript. So we run this. This particular bug, the shellcode that I have in here, it simply spawns calculator. So calculator.exe is what spawns up if it's successful. Now, the shellcode could be changed to anything, of course, but this one, again, is just simply a calculator. This one also doesn't work all the time. So you might have success sometimes, but not all the time. So So I'm going to go ahead and kill this one real quick. Actually, what I want to show you is something a little bit more interesting. See if we get this guy to work. So I'm waiting for a pop-up to appear. We have an action script making a call out to, because action script can't directly access the browser DOM. It has to go through JavaScript to do it. So it calls out to a JavaScript function that triggers the bug, and then JavaScript can do what it needs to do. So a lot of times when it doesn't respond like this, it just needs to be rebooted. Let me go ahead and reboot this, and while I'm doing that, I'll take any questions that someone might have while it's restarting. Yes?
If you spray the heap and you trigger the use after free, it looks like you're just allocating one object of the same size. Is that going to land in the same space, or do they allocate one on one?
It's a good question. So the question is, after the use after free bug, or after the object is deleted and we want to replace it, then do we just create one object? Is that enough, or do we need to do a bunch? That gets into whether or not things like the low fragmentation heap and such are being used, because depending on how many objects of that size are currently stored in the LFH, we may have to trigger the LFH by doing 16, 17 consecutive allocations of that size to make sure that we fill that location. And now, especially with isolated heaps, it gets a lot more challenging. So now that it's started back up, I'll quickly do a check here. Bring up Internet Explorer, connect over to it again. What I'm hoping to show you right here is that the size is modified. So hopefully we'll get a pop-up box here. I'm going to set up connecting to it while I'm waiting. Again, these guys are hit or miss here. So there it is, done spraying heap. So it successfully worked that time. We'll attach to it. And now I'm going to look at the memory address. So DD0x1A001000. So see how it's 3F0 right now? Now watch what happens. I'm going to let it continue. And I'll say OK. And then we'll set to break. Well, it's still spraying the heap there. I should have let it continue. So let me let it go for a little bit longer. So what should have happened here is probably a different setting I need to make, but it should have changed at the 3F, and been much larger at that point. So I got like 2 minutes left. Let me try to connect out to the actual exploit again. That's what happens when you try to cram so much into 45 minutes. So now I'm going to connect back across. And this should be the exploit that spawns up the calculator if it's successful. Just clear my cache to make sure. So we'll click on the trigger, see what happens. Takes a moment, spooling up here. It's doing things like spraying the heap with the flash object and things, so it takes a little bit of time. So how much data would you normally spray? It depends. I mean, you can get precision allocations if you can specify the location where you want the sprays to occur, then you can be much smaller. But a lot of times it's going to be tens of hundreds of megabytes sometimes. But it happens usually very quickly. So this guy hasn't called the little button that I wanted to see. Like I said, it doesn't work all the time. I'll attach to it though real quickly and see if that size was changed. Nope, still not changing that example. So last attempt, and then we'll call it. but I'll be around. I can happily demonstrate it more off the time here. So one more go. It's usually nice to me and works in the last go. We'll see. Any other questions while finishing up here? Yep.
Do you always try to overwrite the object and take control of the B pointer, or do you sometimes just try to find a way to overwrite the old B table?
Yeah, so the question is, do you always overwrite the object, replace the object, or can you sometimes overwrite the virtual function table and do it that way? There have been attacks that do that. It's less likely the ways that things are reordered and placed in memory. It's less likely that you'll be able to do that. But like there was an old example called Internet Exploiter that did exactly that, and it's possible. All right, so it doesn't want to seem to be nice. So any other questions? If not, then enjoy the rest of the conference, and I'll be around if you want to ask any questions or see anything. Yep.
Touched on the new mitigation Microsoft did.
Yep.
What are your thoughts about it?
Right, so question about the mitigations again. They added two. One was isolated heaps, which I kind of explained. If you can find out a way to get object allocations in the heap that's affected. So what you'll see sometimes, and I wrote some IDA scripts that do this, go through and determine what objects are going to go in an isolated heaps versus which ones are in the process heap. If it's still in the process heap, you're fine. If it's in an isolated heap, then you need to do more research to determine if you can force an allocation of an object in the desired heap, and then you'll still win. So it's harder, but it's not impossible. The other big protection they added was called protected free. And protected free goes and says, well, usually people call JavaScript garbage collector to come in and just give the memory back to the heap right away. But this kind of lets it trickle out a little slower, and it says, let's not give it back right away, because that'll hurt people doing use after free attacks. So you can do we've figured out some ways to hit the threshold that makes it release it right away. So there are ways to do it. It's just more targeted now. All right, so again, if you want to see this, I'm happy to sit down with you and show you a little bit more. Didn't get the calculator on the screen, sorry. But thanks for coming. I appreciate it. Enjoy the rest of the conference.